So this video is going to be a very quick introduction to the primary diode types. And I say primary diode types because these three, a rectifier diode, a Zener diode, and a light emitting diode, are actually very similar to the other 20-ish types of diodes, with very small differences in between. Very important differences, but very small. Now this circuit that I've built on the board is fairly simple. It's 4 sub-circuits in parallel, each powered by the 16-volt power supply. The first branch is just a 1K current limiting resistor in series with the small red LED, which I'm using as an indicator of current flowing or not. The other 3 branches also have the same indicator LED, which will not light up until a minimum voltage is reached of 1.6 volts. But in addition to the indicator LED, you also have the voltage drop of the diode that is in series with the indicator LED. So where the first branch will light up as soon as it reaches the LED's 1.6 volts, the branch that has the rectifier diode in series with the indicator diode will not start to conduct until the 1.6 volts from the indicator LED plus the 0.7 volts of the rectifier diode together has been reached. So the first branch will light at 1.6 volts and the second branch will light at 2.1 volts. The third branch with a Zener diode oriented in the forward biased direction will light up when the Zener's forward voltage drop of 0.8 volts plus the 1.6 volts of the indicator LED is reached. So that's 2.2 volts. And finally, we have an actual light emitting diode whose whole function in life, whole purpose for existence, is to efficiently turn electricity into light. This is a white LED, and this white LED happens to have a 2.66 volt forward voltage drop. So the fourth branch will not light up until 1.6 volts plus 2.7 volts has been reached. So if I turn on the power supply and I ramp it up in 1 volt increments, right now it's at 0 volts. If I go to 1 volt, you will still see nothing light because 1 volt is too low for even the indicator LED by itself. When we reach 2 volts, that's above the indicator LED's minimum voltage of 1.6, so it begins conducting current limited by the 1000 ohm resistance. But the branches with additional diodes in the circuit are still below the sum of the voltage drops required. So let's go up to 3 volts. And now the rectifier diode is conducting, and the Zener diode is conducting in the forward direction. The white LED is still not conducting. 4 volts, 5 volts, and we finally get light on the white LED. As we increase the DC power supply toward our maximum of 16 volts, everything will just simply get brighter. But you can see very clearly that the indicator light that has nothing else in line is brightest, followed by the 2 smaller voltage drops of the rectifier diodes. These 2 LEDs together are creating a 4.7 volt drop, leaving less voltage across the resistor. And less voltage across the resistor means less current through the resistor, meaning less current through the circuit, meaning dimmer. I've already measured the voltage drops across each of these components, and the bright red LEDs are each about 2 volts. The dimmer LED is about 1.6, 1.7. The drop across the rectifier diode is 0.7 volts. The forward voltage drop of this Zener diode is 0.8 volts. And the forward voltage drop across this white LED is a whopping 2.7 volts. So now we're going to turn off the power supply, and I'm going to reverse these two diodes and the LED. So this is the circuit redrawn with the LEDs oriented in the reverse biased direction. Same thing with the Zener diode, the rectifier diode, and the white LED. The indicator LEDs I kept exactly the same. So if current flows through any of these branches, the indicator lights will light. I haven't written numbers here yet, and there's a very important reason for that. The reason is some diodes are designed to be able to conduct in the reverse direction, notably Zener diodes. This Zener diode is manufactured with a reverse breakdown voltage, which is called the Zener voltage, of 10 volts. So this branch is going to start conducting once we reach the 10 volts of the Zener plus the 1.6 volts that is required to turn on the LED, but not before. This rectifier diode, I know for a fact, is not going to conduct. This particular diode is a 1N4000 series, the 1N4001 specifically, and it has what is known as a peak inverse voltage of 50 volts, which means that it is designed to not conduct and has a maximum inverse voltage rating of 50 volts. Above 50 volts, you will eventually have this conduct, and when it conducts, it will probably damage itself in the process. This is why the 1N4000 series has a 1N4001 that has a peak inverse voltage of 50 volts. It has a 4002 that can handle 100 volts, and it goes all the way up to a 1N4007 that is designed to handle a reverse voltage of 1000 volts. Totally depends on your application. Zener diodes also come in different voltages, but they're not peak inverse voltages, they're called Zener voltages, and they are designed to conduct at that voltage. LEDs are only designed to be driven in the forward direction. They are not designed to handle a lot of current. The reverse voltage that they can withstand is not very high, and once you reach that, you may briefly see a little bit of light, and then you will see nothing, and the LED will be damaged. And so I'm going to ramp up the voltage towards 16 volts, and it may be interesting, and it may be completely boring. Let's find out. So as before, we're starting off with 0 volts, and we're going up in 1 volt increments. So at 1 volt, not even the first branch lights. At 2 volts, the first LED turns on. At 3 volts, 4 volts, 5 volts, 6, 7, 8, 9, 10, 11, 12 volts, the Zener begins conducting. But the rectifier diode is still not conducting, and neither is the LED. 13, 14, 15, 16 volts. Now, measuring these voltages is going to be a little tricky, because if you have zero current flowing through a circuit and you try and measure it with a standard multimeter, the multimeter's internal resistance will cause weird values. So rather than just going across the rectifier diode, I'm going to check the voltage across everything except for the resistor. So the rectifier diode plus the LED is 15.6 volts. the Zener diode plus the LED is an even 12 volts. And the white LED plus the indicator LED is 15.6 volts out of 15.6 volts. So the fact that the voltage of all three components together is the same voltage as just the two LEDs together means, yes, there is essentially zero current flowing through that resistor right now. And if we subtract the 1.6 volts from the components that aren't lighting up, and we subtract the 2 volts from the LED that is lighting up reasonably bright with the Zener diode, we get exactly what we expect. Now, just to clarify, although the power supply is putting out 16 volts, my meter, with its slightly inaccurate measurement, was actually reading 15.6 volts across all components. So we can consider this to be 15.6 volts across each branch. The 15.6 volts minus the 1.6 of the LED is the voltage that is across the LED or the rectifier diode when it's reverse biased. The Zener diode is not 14 volts, it's 10 volts, and it happens to be a 10 volt Zener diode. Now, if you do the math, what you'll realize is that if my meter was measuring 0.4 volts below the 16 volts that the power supply is actually putting out, that also means that the true voltage across the Zener diode is probably 9.4 volts. This will become more clear in assignment 2, but suffice to say, the Zener's voltage drop at its Zener voltage, similar to the LED's voltage drop, changes based on the amount of current going through it. So when it first turns on, the LED is showing 1.6 volts. By the time it reaches 15 or 20 milliamps, it's at 2 volts. With the Zener diode, a Zener diode does not instantly turn on and stay at exactly 10 volts. It will be 10 volts at some specified current that you can find in the datasheet. But it will vary with current. So in our case, the Zener voltage at the current that's currently passing through this branch of the circuit is 9.4 volts. With a higher current, this would be a higher voltage.